So my name is Soham Chatterjee. I'm a student of Chennai Mathematical Institute. I'm doing BSc in Math and Computer Science. Uh, Today's talk will be factorization of polynomials, but using algebraic circuits. It is basically a overall survey of whatever the major results we have got till now in factorization of polynomials. These are the topic we will mainly cover. I will describe in much detail later. So now what is complexity theory? Basically, we want to study Turing machines and we kind of separate all the problems in different, you can think of boxes, which we basically call classes. Now now this separation is done based on many things like if a problem is solvable or not, and if it is solvable, how much time it takes, how much space it takes, or if someone takes at each step randomly, can he solve the problem? Or if I communicate with another computer, can I solve the problem? These kind of things. Here we will mainly look at the model circuits, which is basically a directed acyclic graph. But here we have only one root, and we start from bottom, the leaves, and start computing at each level. We compute the tree and reach the root, and finally whatever the computation we get, that's the value of that circuit. So in Boolean circuits, you may know that basically there are and not gate, no, and or gates, and each edges have this not symbol or nothing typically. So you start computing from things, and suppose here x1, x2, and this or so what x1 or x2, and so the value at this OR gate is x1 or x2. To compute like this, and finally whatever the output, whatever the final boolean formula we get at this top gate is basically the value of 5. So similarly we consider these algebraic circuits where instead of and or gate we think about polynomials. So basically what we do, basically the plus and multiplication we use instead of and or gate, and in each edge we use the coefficients which basically from a ring which we defined previously for that circuit. Why we study these circuits? You see, Boolean circuits have only two inputs, 0 and 1, but that restricts us too much, and that's why we cannot say much about those circuits. So that's why we kind of go to algebraic circuit where we have a lot of inputs, which is a whole field, FP or anything, any characteristic zero field, suppose Q. So you have infinitely many possible inputs. So there we try to study the circuits, and if we get anything good result and try to relate that result to Boolean world. So that's why we mainly study algebraic circuits. Now, polynomial factoring has several applications in the world of computer science. In coding theory, you use this in Reed-Solomon codes, Reed-Muller codes. Also, it is used in cryptography, integer factoring, many things. You can see at these references to find those. So another note that in old papers on algebraic circuits, they used to mention this term straight line program. So since it was old, they didn't have any particular name for this model, so they just used straight line program. Mainly Caltofan and Valiant's paper use this term. Now, before we go into much detail, we will mention some definitions. Uh, the size of a DAG, or size of a circuit, is basically or number of all nodes or number of all edges. Even sometimes we just think number of all nodes plus number of edges. That's actually kind of gives more meaningful definition. But it actually depends. I mean, not much changes, but still. Now, fan in and fan out basically in degree and out degree, nothing much. Here, now we will talk about two models in this algebraic circuit. First is ABP. Here we have a source vertex and a final vertex, and you take every possible path. Now, every possible path gives a polynomial, and you then sum over all such paths. Now, how do you evaluate every possible path? So, each path has a edge, and in each edge you have a linear polynomial or a coefficient or a constant. So, at I mean, in each path, for each edge, you take those linear polynomials of constants and you multiply those. So the final polynomial you get in each path is the value of that path. Then you sum over all these, and what find the final polynomial is the final polynomial is represented by that model, and that model is called ABP or arithmetic branching problem. Another model is formula, which basically a restricted version of general circuits. The circuits have multiple, I mean more than one fan out, but formula has only one fan out. So it is worth mentioning that in formulas you cannot reuse any computation. Suppose till a node you have done some computation. Now in general circuits you can use that computation in two different locations. But in formula you cannot do that. Whatever you have computed till now have to be used locally. You cannot reuse that. If you have to use that, you have to again compute all those things separately from start. That's why formula gives us much more trouble. Now we will mention some classes in algebraic circuits. VP. VP is basically set of all circuits which has polynomial of n degree and polynomial of n size. By the way, n actually denotes the number of variables. From now on, n basically means number of variables. VP is basically P analog of algebraic circuits. VVP is kind of same set of all AVPs which has degree polynomial of n and size polynomial of n. VF set of all formulas, degree polynomial of n and size polynomial of n. Now VNP. VNP is the NP analog of uh, algebraic circuits. So basically you have a polynomial Fn. Now you have another polynomial which actually means the number of all possible variables. I mean set of all basically here see the 0 comma 1 whole to the power tn. So tn is a value. So you have that many w. Now whenever you are having 0, you are missing. I mean you are not considering those. I mean w basically you have 0 comma 1 whole to the power tn. So that many w's you have. So that many variables you have. Then you introduce another family gn where you sum over all possible these n, a gn, and then evaluate the polynomials in those variables and you sum over all those. So basically it kind of gives out a NP definition vibe. So that's why VNP is NP analog. Now some small results that VAP is in VVP and VVP is in VP. I mean, it is actually very easy if you see. I mean, if you try to construct a formula and branching program, you will see that it is just takes a polynomial here. And from VVP is in VP. Basically, VVP. I mean, you can see here down here the determinant is VVP complete. This result is in Meena Mahajan's paper. You can see that now determinant has the polynomial size circuit in VP. So that's why we have VVP even VP. And VP is in VNP, I mean, that's obvious. Another result that any circuit, for any circuit of sizes and depth D, you can convert it to S to the power D. Basically, at each level, at each node, can have at most as many edges going out from it because we have sizes. So at most can be as many nodes. So you have that many. You have to make that many copies of that node. So you will do this at each depth. So at each depth, whatever there, you have to multiply by s. So that's how we are getting s to the power b. Now this is not a result but a hypothesis that we believe very much. And if you prove, this, this VP is strictly containing VNP has a value worth like P not equals to NP. Because you can, the next result you can see that if VP equals to VNP, then permanent has polynomial size circuit, then sharp P becomes FP because since you have a polynomial size circuit, you can easily compute permanent. And if you compute permanent easily, you have P equals to NP. Now, since we have talked about permanent, permanent is VNP complete, and this result you will find in Bourgeois, this completeness and reduction in algebraic complexity theory book. There is another book of Bourgeois which is algebraic complexity theory. That's also very good. I mean, very good starting book for algebraic circuits. Now there are also some other structural results like if you have a polynomial, then ith degree homogeneous part, how will you calculate it? Or differentiation of a polynomial, how will you compute it? So they take the polynomial blurb and you can read those things in these two surveys. One survey is of Ramprasad Saptarishi and another survey is joint work done by Amish Pilka and Amir Yahudaya. Both these two surveys are very good. You can start reading them. Now, before we going to factorization, we will mention some mathematics. Basically, two specific tools which we need: Newton integration and Hensel lifting. Newton integration is basically if you both these roots are basically actually both these theorems basically approximates the polynomial. Newton integration mainly approximates the root, and Hensel lifting approximates the polynomial in a factor you can say. So basically these theorem now yi basically means that if I have G as a root and I delete all the degree I and higher terms of G, then it will be equals to YL. That's what basically it means. So you will approximate degree wise from 0 to higher. Now, before using Newton integration, many times you will see that we have brought a new variable y, which basically we do a random shift. So by Schwarzschild lemma, if you have read that a polynomial evaluated at any random point has a very low probability that it is zero. So that's why we actually random shift so that it has a very high probability that it's non-zero. You can read about Schwarzschild lemma from this fast probabilistic algorithms this paper. Now Hensel lifting. Now Hensel lifting is, I mean, first we what is the lift? So if you have factors g and h modulo I, then such that g or h are co-prime, then modulo I co-prime, then you have g dash and h dash which are factors of f modulo I square, and modulo I they are basically g and h, and modulo I square they are co-prime. So this is what we call a lift. So what is Hensel lifting? Uses this definition, and what it means basically is there are possible that multiple many lifts are possible. So all those lifts are interrelated by a multiple of units basically. And if you make monic all those lifts, then it there will be only a unique lift. Now, while doing monic, you have to do division. This is a division gate. Now, removing a division gate is very easy for circuits, but for formula and ADBs, it takes a huge blow. It's a run result that it takes a very high blow, exponential blow. Now, unified circuit, we will do get, I mean, each factor will have multiplicity 1. So whatever a single factor, I mean, I will get, it will be irreducible. We can easily claim that a factor will be irreducible. Now there we will do very easily, because if you take GCD of f and delta f and repeat this process till you get one, fine, then you can be sure that f and delta f has no common factors, which actually means that f is equal to. Then we will do distinct degree. This step actually does that. Suppose I, then it distinct degree gives us all the product of all I degree irreducible factors of F. So what we, I mean, if you have read field theory, this theorem that h to the power q to the power d minus x gives the product of all irreducible polynomials whose degree divides d. So if I do it from 1 to d by 2 and separate all those factors, then suppose I at I after ith step we don't have any ith degree factors. So if I get that to the next I plus 1, we will only get all the product of I I plus 1 degree irreducible factors of A. So that's how we get a product of all I degree irreducible factors of A after this process. Now we will now bring out all the each irreducible factor. This uses Chinese remainder theorem on ideals and rings. We don't need that much. We basically only need this statement that fx mod fx quotiented by fg is isomorphic to fx quotiented by f, direct, and fx direct product of fx quotiented by f and fx quotiented by g. Now we will talk about Barley-Camp algorithm, which is the one of the oldest algorithm of polynomial factorization. You can read this from this Gathen's book or Chatterjee's survey. Now, first, that fx quotiented by f, fqx quotiented by f by Chinese remainder theorem equals to this ring A, because f equals to product of all these fi. So we know the right hand side ring, but we don't know about the left hand side ring, and we want to factorize the left hand side ring. So we actually want to find the isomorphism between these two rings, and if we get it, we have done that factorization. So for this we will try to find a g in the k tuple such that g to the power p equals to g. Now this g gives us a factor of f, because g to the power p equals to g means each of the elements in the tuple are in fp, and that means g to the power p minus g factorizes as g minus alpha, where alpha is in fp, and product of all such g minus alpha. This is 0 mod f, that means f divides this, that means product of all fi divides product of all g minus alpha. Now see the g, these set of g in fqx forms a vector space over fp. So you can see we have to do some linear equation solving to get a g, and then we will do for each alpha we will just take a GCD of f and g minus alpha and gives a factor. If the time complexity of this whole thing takes O tilde of p into dn to the power omega. This omega is the matrix exponent, matrix multiplication exponent, which we get from the smallest exponent of complexity in producing the two matrices. That's where the omega is coming. Now we have done much improvements in univariate factorization, but with the addition of randomization. Now, randomization is a very powerful thing, or we do it actually helps us to do many advanced or hard solve hard problems, but just a little randomization solves it, and we get a very high probability that we have the correct result. Before this, we have this. I mean, we know this theorem that in FP star, the half of the elements have are quadratic residue and half other half are non-quadratic residue. But there are no pattern of these quadratic residues. If we do this, if we find a pattern, we actually solve all these randomization problems. So the probability that any alpha taken randomly from FP star is a quadratic residue is half. So what Cantor-Zassenhaus algorithm do is take any a randomly from FP, then shift g equals to f minus a. Now see g have now g have different quadratic residue because we have taken, I mean, we have shifted a randomly. So any 0 of fx minus f of a g equals to fx x minus a. If it is a square, then it is also a root of GCD of this. That means if now we cannot shift it like this, so we what we'll do that take the GCD of fx and x plus a whole to the power p minus 1 by 2 minus 1, and it gives us very high probability a factor. So the time complexity is basically O tilde g to the power omega log g. Now these two are main algorithms for univariate polynomial factorization in finite characteristics. Now we will talk about finite characteristics, I mean characteristic zero fields, mainly QX and ZX. So this algorithm is discovered by Leinster, and Lovacic. It uses computing shortest vector in a lattice, kind of doing approximating. I mean, not exactly computing, but approximates the shortest vector. This algorithm is also called L-cube algorithm. Here, I mean, we assume that coefficients of f are less than 2 to the power l minus 1, and I mean this f infinity norm of f, which means the maximum coefficient modulus of coefficient is a. So then we get these two bounds. On first bound is on a root of f, and the second bound is on a factor of f. And this bound, I mean another bound which actually gives bound on a f and g based on m. So now the main algorithm L cube is basically first you do the pre-process to make f square free. Then you find the smallest prime p such that f does not define the f a p does not divide the highest degree coefficient, and f is also square free modulo p. Then it uses Barlecamp to factorize in mod p, where G0 is obviously irreducible. Then it Hensel lifts with respect to P. So the idea generated here is P generated by P, and lifts for this log 2 into L many times. And then we get that GK HK lifts. Now we try to find the G tilde LK such that G tilde equals to GK LK, and this fourth step actually where we use the shortest vector thing. Now finding a shortest vector in general lattice is NP hard. You can see this paper. and even constant approximation of it is also NP-hard. But here we only need 2 to the power n approximation, which is actually doable in polynomial time, so nothing to worry. And finally, we output the GCD of f and GP. Its complexity is high. You can say n to the power 10. Still, it's a polynomial. So, okay, with it. Now we will go to the multivariate polynomial factorization. So, in multivariate, we most of the time we cannot do factorize these directly. Even if we, I mean, in degree the univariate polynomial, number of monomials is d at most. But in DVD multivariate, if variables are n, then number of degree d monomials is n plus b choose n. That's also very high. So that's why I mean we cannot go to the monomials. Most of the times, what we do that we do a random shift, introduce a new variable, then go to the univariate polynomial with respect to that new variable, factorize there, then try to lift. So you can read surveys on polynomial factorization from these Chatterjee, these two surveys, and another surveys of Forbes and Spilker. You can start reading this to get much more depth in polynomial factorization. First we will do is low degree polynomial factorization, which is the result of Raphael Oliveira. Here low degree means each degree, individual degrees are bounded by some constant. So if individual degrees are bounded in obviously characteristic zero field, then we get a circuit or formula of a factor in size for nr whole to the power r s, polynomial of nr whole to the power r and s, and depth increases by 5. It is a huge result because it is the only result in formulas, which is talking about factorization in formulas. So it actually uses Newton iteration carefully to compute till ith degree homogeneous part of the polynomial and kind of does like that to find the approximate factors. Now we will talk about closure of the classes under factorization. VP is closed under factorization. This result was proven by Chow, Kumar, and Spilka. I mean, sorry, Solomon, and also done by Kaltofen. Kaltofen's result is actually old, but that proof is not enjoyable to read. This Chowkumar and Solomon's proof is very enjoyable and beautiful proof. Another result they have that if f equals to g to the power e, then compute g. Now we come back to PDP fact closure. This paper is done by Amit Kumar Singh and Thomas Theodore. They use the same strategy, go to univariate, then do factorize there, then do Hensel lift to get a factor, approximate a factor. But here the problem is Hensel lift doesn't preserve monicness. But originally f equals to g as g is monic, and when we consider univariate, there g0 is also monic, but the lifts are not may not be monic, and we cannot do make it monic at each lift because as I said before that making it monic means introducing a division gate, and removing a division gate is basically takes a huge blow up in ABP and formulas. So what he did that he didn't made it monic. In the end, when all the lifts are done, he done a system of linear equation solving to get the exact factors. Basically, uh, basically by system of linear equation, he tries to find that exact unit which actually gives us the factor. Now here are some more factorization results that if f equals to u0 into u1 and size of f and size of u0 are bounded by s, then you have a polynomial size of factors of u1 in s plus degree of square root part of u1. And it is even true for exponential circuits. That's actually what makes it much more important result. We have also closure results for VF, VDP, VNP. For I mean, if I have a factor, if I have the original polynomial f, then the factor size will be polynomial of n to the power log n. And they have kind of showed that we cannot make it better because they actually uses Newton iteration. And if you remember, Newton iteration uses here they are using the same old computation. Again, they are using here, and then they are evaluating that in yi, and the same evaluations are again used in yi plus 2. So they are using same computation again and again, and we in ABP and formula we cannot reuse computations. So that's why we have a blow up in results. So they have proved that we cannot make it better here. And this paper is done by Pranjal Datta, Nitin Saxena, and Amit Kumar Sinha. You can read that paper. They have also shown same closure results for approximative classes. Approximative classes is basically previously we have taken the coefficients from the field mentioned field, but here we will take coefficients from introduce a new variable, suppose epsilon, then take the rational field f of e. So here, suppose previously you computed f, so here you are computing f plus epsilon into f1 plus epsilon square into f2 plus epsilon cube into f3 and so on. Not an infinite series, still a finite degree. But here the problem is you cannot put 0 to epsilon because I mean in the circuit there may be some edge where it uses a rational function of epsilon, and if you put epsilon equals to 0 it becomes meaningless. So that's why I mean approximative classes are also very important. And there is a result that VF closure equals to with to ABP closure. It kind of relates the VF and VBP interlink. So this thing, I mean, this result is also very important. Now, these are the main multivariate polynomial factorization whiteboards, which means we can see the circuit structure of the polynomial. Here we have a black box multiplication where we cannot see, or you can think we have an oracle where we give a point and oracle gives the value of the polynomial and the this uh, factorization algorithm mainly uses it's a randomized one. It mainly uses Hilbert irreducibility theorem. You can read this theorem in this Caltechon's paper. These two Caltechon's paper actually this paper is also very good, and or you can read from Saptash's survey. Basically, what this theorem means is if I have a polynomial, suppose reducible, and I randomly project that polynomial into a two-dimensional space, then that polynomial still becomes reducible and with very high probability. You can see here O of d to the power 5 by S, cardinality of it. So basically what this means that if I randomly project to a two-dimensional space, the number of irreducible factors remains same with high probability. So that's how they actually randomly project, and then their factor. I mean, in that plane, they factorize normally univariate. Factorize. Go to the univariate factorization, univariate polynomial, then factorize there, then himself leave to get a bivariate factorization, and finally leave each factor to the whole space. So that's the main black box factorization algorithm, and this algorithm gives a right answer with at least O of d to the power 6 by cardinality of s probability. And if you take the s very high, it certainly gives. If you take the size of s very low, then you have a very high probability that you are getting the right answer. Now, these are all the main factorization results we have found till now. There are many other results also, but these are the main to get start in this field. Now I will mention some open questions like we don't know if we can factorize the univariate polynomial randomly in O tilde of d log square cube complexity. We cannot say anything about factors of VF closure, ROABP, and constanted circuits. We know nothing about these models. We don't know any algorithm to find the ABP factor. We have given the existential proof in the Amit Sinha paper, but we don't know any algorithm. We don't know any bound on the pth root of a polynomial in FPX. Basically, if you have f to the power p, a circuit for f to the power p, then we don't know if we can say anything about f. That's also we don't know. You can see one difficulty of using here that if you differentiate f, it will become zero because we are taking in fp. And many other things makes it very much complicated. And the last is the factor conjecture that we remove the dependence on d and make it dependent on the degree of the final factor. That we have randomized algorithm to find a factor in polynomial of s, n, and d, but we don't know if we can remove the d and make it dependent on the final degree of the factor. That's the factor conjecture. So I have mentioned all these references here. You can read from here. This book I mentioned early on the talk that Algebraic Complexity Theory by Purvita is a very good book, and this also a good book, Completeness and Reduction. It mainly talks about the classes. You can also start reading this book, Modern Computer Algebra by Gathan and Gerhard, which is a very good book for computational algebra and number theory. Uh, you can read more about Hensel lifting and Newton iteration from this Gathan's paper, Hensel and Newton methods in valuation games. And also they are here, modern computer algebra. You can read those two things from both these two. Here you have a paper on relating uh, Riemann hypothesis, general Riemann hypothesis with factoring polynomials, and you the Barley-Camp algorithm that is mentioned in very detail in this Donald Knuth's book Art of Computer Programming Volume 2. You can see that it's very well written there. Uh, you can read about the L-cube algorithm from this Factoring Polynomials with Rational Coefficient book written by Leinster and Lovarty. I have also added this algebra and computation. Ramprasad Saptarishi's course on algebra and computation. It's a course he took in PIFR on 2017. Their notes are publicly available. You can read that and start learning about computational algebra. And I have added all other papers also. You can read those things. You can read Cantor's section from this paper on Hensel factorization paper. And obviously this survey is very good to start on arithmetic circuits by Schwilk and Yaldo. That's all. Thank you.